So I'm Art Bragg. I'm an assistant professor in the chemistry department at Johns Hopkins. My area of research is in energy transfer and charge transfer in molecular systems and materials. We're very interested in understanding pathways for moving energy about in material systems down at the molecular level. The types of materials we'd be interested in are things like organic photovoltaics or organic light-emitting diodes. These are materials that are made out of condensed or aggregated organic systems, and so then one has to be concerned about how does energy transfer between molecules or charge transfer between molecules in these systems when they're excited with light or potentially with an electrical current. The type of work that we do is sort of fundamental in nature. We're interested in understanding very basic processes in organic materials or materially relevant systems. So we use lasers to initiate photophysical or photochemical dynamics in these material systems or molecular systems, and then interrogate those dynamics, again, using light pulses. The type of technique that we use is often referred to as a pump probe type technique. There are a lot of variations of this where you initiate some process with a laser pulse and then you probe what you've done to your system at a later time using another laser pulse or set of laser pulses to do some sort of optical process. As you've probably already learned from this video, right, is in pi conjugation you have essentially the basic explanation is that you have pi or p orbital overlap between adjacent, typically carbon sites, but not necessarily always carbon, that give you electron density above and below, typically a plane of your molecule. So the type of systems that we look at are conjugated polymers and conjugated oligomers, and typically these are ring systems, and so pi conjugation ends up as electron density above and below the plane of the molecule. And so with pi conjugation, you can actually have very delocalized electronic states in materials that can cover very large distances. We're interested in fundamental energy transfer and charge separation mechanisms, and how these things depend on the way molecules are, based on their structure, whether that's conformation or the way that they pack with other molecules. If you're talking about material morphologies is a common word to use. So when you put conjugated materials together to make a device, they pack, and how they pack can impact how energy or charge separates. So the pi conjugation is very important for conjugated polymer materials because essentially it allows you to control, it's intimately related to the band gap of the material. So very conjugated states, something that you'll learn in physical chemistry, is that essentially the longer the distance of conjugation, the lower will be the energy for exciting an electron to a higher electronic state. So this is a way that you can harness photons from the sun or from whatever light source by exciting these molecules to higher electronic states. And once you've done this, you can then harness an electron from that lowest unoccupied molecular orbital and charge separate from a conjugated polymer so that you can get an electrical current. So you ready to see the lab?
Show us the laser.
So now we're inside my laser laboratory. So this is where we actually conduct experiments to study energy and charge transfer in conjugated molecular and material systems. The way these experiments typically work is that we initiate some sort of photophysical process in our material through excitation with light. So in terms of the pi conjugation of organic systems, we would be promoting some conjugated molecules to an excited state. So promoting an electron from the highest occupied molecular orbital to the lowest unoccupied molecular orbital, which creates very delocalized electronic states in these materials. And what we're interested in is understanding how structure affects the dynamics of relaxing that energy, either through energy transfer or through charge separation to other materials that are nearby. And the way that we probe that is we use a second laser pulse at a specific time delay to interrogate the spectroscopy of our system. So whereas our first excitation pulse promotes electrons from the HOMO to the LUMO levels, we have a second pulse that arrives very short time later that will then interrogate transitions from that LUMO to even higher lying molecular orbitals of the system. We control this delay between the two pulses down to timescales of tens of femtoseconds, which is 10 to the minus 15 seconds, so very fast timescales, because these are the timescales on which bonds vibrate in molecules. The impact of this research is directly within the area of developing new materials for harnessing solar photons for energy applications. A common interest now in organic conjugated polymers and materials is for use in organic photovoltaics or solar cells, where you can take light and separate excitations in organic molecules into electrons and positive charge carriers as well, so that you can collect a current. We're interested in basically answering very basic questions about energy transfer and charge separation in these materials that are important for building device architectures that will have good efficiencies and good value as a solar cell.